that.
Okay, thank you very much for coming to this meeting. Thank you, Carlota, for accepting to share your initiative granted by IEEE Education Society. Me as Vice President Educational Activities found this project very interesting and accepted to get this awarded. And I think from what I can see, we are really happy about all the results, and this initiative is going worldwide. Thank you, Carlota. So we endorsed as this project, me as VP Educational Activities, and Luis Felipe also the Vice Chair of Virtual Graduate Study Consortium. And I'm inviting you to go to this to know more about what is Virtual Graduate Study Consortium. Carlota is contributing to the Virtual Graduate Study Consortium. I'm sharing this screen also. I don't know if you can see this slide about the presentation I made. That can be also found in the at our website of standard development. We'll share with you the link that you can go to see the entire presentation I made that explain broadly what is Virtual Graduate Study Consortium, sponsored by Education Society, Industrial Electronics Society, Standard Association, Computer Society, and many other to come. I'll go very quickly. What is Virtual Graduate Study Consortium? It is mainly a virtual organization, and the details you can read in the this presentation that is accessible to our standard development website. One thing I will go very quickly because we have only few minutes, 5 minutes, and we'll get Carlota will get the floor after that. So this idea of Virtual Graduate Study Consortium came into our mind because during our standard development of IEEE Education Society I chaired, we were able to get an award winner standard on network with smart learning object for online laboratories. This also can be found the details of this standard that is developed. So and we are also working now on another security and structured learning system that I started as a chair, and it is ongoing. We have since then 2 new other standard being developed by IEEE Education Society. Thank you to Luis Felipe leadership for taking the process after me being the chair of standard committee for many years. So the idea came when during the process of standard development, we had some people, students and their academics and industries participating. And at the end, we got now many graduate PhD students that are already graduated, but they were in the process of online laboratory. So I'm inviting all the academics in this call and students also to take part of this strategy of getting university out of the university. What I mean is that it is possible to make a TS a PhD or any end of year project, because we said Virtual Graduate Study Consortium, but we have also undergraduate students invited that can be participating. If you have interest of taking part of this drive, please let us know. Myself, since I was student in end of 70s, I was member of IEEE, so student can benefit being IEEE member. So I will stop here with this image, and you can get all the presentation online through the link that we are going to provide you. So for academics and the industries in this call, we are also inviting you to come and to show interest if you are interested to be a member of IEEE Education Society Virtual Graduate Study Consortium. And Carlota is giving us a lot of insight through the so we have students participating in our teachers, researcher, manager of training, and other. So we have also industries. Labsland is one of the sharing on live labs through the world. The owners participated as students when they in the process of the online laboratory consortium. So you can see also Repub IT is also another industry working with us. And we have also, so just send us the information, what you are, why you are going to, you want to be member of the Virtual Graduate Studies Consortium, and we will get you in. So thank you very much for listening.
So I believe I go next.
Yes, you're next.
Thank you. Thank you, Dr. Hamadou. And thank you, everybody. I don't have slides, but I just want to share a couple of words with you today. My name is Luis Felipe Zapata Rivera. I'm the chair of the IEEE Education Society Standards Committee, a part of IEEE that is in charge of producing standards related to education. And we are really happy to be here and to share with you this morning during this workshop. I want to thank to IEEE Education Society educational activities with the lead of Dr. Hamadou Salih Hassan that really has opened the possibility for collaboration around the world of groups of students and faculty members to talk about education, to have this type of workshops where students have the possibility to interact and to learn something new. I want to thank to the group of students distributed around the world today connected to this meeting that we really appreciate your dedication and your commitment for attending this type of events. And especially to Carlota Berry, Dr. Carlota Berry, that is with us today, sharing her experiences in making available and accessible robotics for STEM, especially for students that are interested in this area. And as she has said in some of her many interviews that I have the opportunity to listen, she had the inspiration from when she was taking a class of, I think, microcontrollers or robotics, and she was a student. And as a student, it was very hard to even get the opportunity to touch, to manipulate one of these devices. And she surely, over the years, being a professor and a researcher, has created this technologies and make it scalable, low cost, and accessible for everybody. And this is a great opportunity that we should take advantage of. So thank you everybody for this, and thank you Carlota for being today with us. Thank you so much.
Thank you so much for having me. Hamadou, did you want to say anything else before I got started?
No, go ahead. You have the floor.
Thank you so much. And thank you, Luis. And I am going to share my slides now. And I want to thank you all for inviting me to speak today. When I applied for this educational initiative, it's because I just knew that I had something great here. 1 second, I want to make sure you can see the slides before I start. Can you see the slides yet?
Yes, the
Yeah.
slides.
No.
Yep.
Your
We see a web page.
Okay, oh, it's the website. Okay, the wrong screen connected. Give me 1 second. Let me change the screen. It connected to the wrong screen. I do apologize. Okay, hopefully you can see it now.
Yes, now we can see.
Sorry,
Okay.
I have to stop my. Go ahead.
Okay. Okay. So I'm going to keep the chat open on one window because I am going to be asking some questions to help tailor my talk. I kind of have to know a little bit of expertise, how much experience people have. But I just really want to thank the IEEE Educational Society for funding my initiative for Robotics for the Streets. This was an idea that I came up with during the pandemic, and it was to design open source, open software, open hardware robots that were 3D printed. And Robotics for the Streets means taking them out of the classroom and making them accessible to communities everywhere, as well as in the classroom. So I'm a professor of electrical and computer engineering at Rose-Hulman Institute of Technology, which is in Terre Haute, Indiana, in the United States. And I have been a professor there since 2006. My PhD is in human robot interaction, but now I focus more on robotics education at all levels, because I think robotics presents a wonderful opportunity to get people excited about the possibilities of science, technology, engineering, math, and also art. So I use STEAM and STEM a lot in order to talk about both of those are exciting opportunities for us. So my learning objectives for today's workshop is that at the conclusion, you should be able to define a robot as well as the parts of a robot, explain robot control architecture, describe steps to implement artificial intelligence and behaviors on robots using the Sense Plan Act robot primitives, and discuss how to use open source robotics to meet IEEE standards for network smart learning objects for online laboratories. So my STEM is for the streets, and robotics from the streets, like I said, is based upon my desire in order to diversify and see more diverse populations in STEM and engineering. In a more global society, we need all voices in the room. So I do this through robotics in order to use robotics to educate and diversify the profession. And I do this by doing workshops and talks and being the visiting scientist at the Children's Museum for adults and children. So the IEEE standard for networks smart learning objects is based upon this relationship between components, hardware, software, and learning environments to ease the design and implementation of pedagogically driven online laboratory activities. So this ties in very closely with low cost open source robots, because now at a low cost, if we can get more robots into the hands of the users, they can now connect with them wirelessly, connect online, or have virtual laboratories built around this platform. And these things can be done through the labs as a service, learning objects and clients, or even massive online courses or laboratories as well. So it's an experiment that is a scientific procedure that has a test, hypothesis, and demonstration, has hardware to perform the experiment, and a learning activity to acquire skills. At my university, I teach mobile robotics in a flipped format. So the students actually do a lot of the individual learning online. And then when they come to see me, they demonstrate that the robot is able to achieve some task. So it's a little bit of this, but it's also a little bit of in-person engagement as well. So an online laboratory is accessible via a computer network. And I also forgot to turn my captions on. So please give me 1 second I want to make sure the captions are on. I think they should be on now. Here we go. So an online laboratory is accessible via computer network as virtual, remote, or hybrid. You can also have remote laboratories where physical devices are observed or controlled at a distance in a real time or batch. Or you could have a virtual laboratory where interactive simulation of physical phenomena are supported by mathematical models or experimental data basis. So here, once again, is this image that illustrates how this would work, where it establishes the relationship between the components as well as is pedagogically driven online. Okay, I don't know.
Please. She's back, so let's wait one more minute.
I am so sorry. The internet at my house just went down, but it just came back up. Sorry. I am so sorry about that. Hopefully, it does not happen again. Let me reshare my screen and I'll keep going. That happens sometimes. This was the most horrible time for that to happen, unfortunately. Okay, I am turning the captions back on. I'm sorry about that. Guess it's a good thing I made you guys co-host, because then when that happens, you can still stay in the meeting. Okay, so on to the next slide. So an online laboratory fits in learning frameworks, pedagogic context in terms of a learning object. So this would be different from a remote control interface because it includes a lab assignment, course content, external content, and assessments. During my presentation today, I will give you some tidbits of how I do this with my courses and what kind of lab assignments we do. And ideally, we're going to do a few today, depending upon how our time goes. So I'm going to do that as well. When I started back, I lost the chat. So I got to get the chat back because I am going to be asking some questions and I need to see your answers once I get to that point. Okay. All right. So here is an example of how my students do remote learning. So because I require them to do a software design plan before they do the actual lab, they have to either simulate it, they have to do either a flow chart, a state machine, they have to write some sample code, pseudocode, or something like that. So ways they
I'm
have
sorry, somebody else took the screen, so we cannot see your slides.
You can't see the screen anymore?
No, it's now we see a notepad information about the link to the meeting. Now, yeah.
What about now?
Yeah, now we can see you.
Oh, okay, I'm so sorry. Okay. So it must have changed out when I came back. Okay, so here is an example of one way my students do software design plans virtually before they actually do the actual lab. So they do Tinkercad.
Sorry, Abdulaziz, you are sharing your screen. Please stop.
I thought I was sharing my screen.
Yeah, but I saw someone from Niger sharing the screen. I cannot see your screen.
Yeah.
Okay, I'm going to try it again. Let me try one more time and tell me what happens. I turned off multiple sharing. So now, what about now?
Yeah.
What do you see now?
Now we can see you.
Okay. All right, Maria, did you need something as well?
No, I'm good.
You're good.
I was gonna say something about the interruption.
Oh, okay.
Abdul, it looked like Abdul was sharing something.
Okay. I have now turned off sharing, so I'm the only one that can share.
Perfect.
Okay. So, all right. So let me get the chat back open now. Sorry about that. Okay. So here's an example of how my students do a pre-lab using learning objects online before they do the actual physical lab on the robot. And I will tell you that the robot they use in class is not the one that I shipped everyone. They use a robot that is a bit more expensive, obviously, but still the same thing applies. So one of the labs they do is called bang bang control or wall following. So here's a simulation of what that looks like. I'm going to forward a little bit because I don't want to play the whole thing, but turns and forward and spin moves until you're within the correct distance to the wall, and then you just move straight ahead. The other point of bang bang control happens when I lose the wall. Then I have to once again hard code a movement to get the robot to catch back on the wall, and then it goes back into on off until it collects all the coin. Please watch and enjoy. This is the Dawson Virtual Laboratory. It's one example. They can write Arduino code because their labs are in Sketch code, and they're testing their wall following algorithm, and they know that they're within distance to the wall if the robot can actively collect the coin. So it should not be hard coded. They should have some kind of behaviors like an if this happens situation. So here's an example where the robot loses the wall because there's no wall there, and can it catch back on and continue to follow and collect the coins. So this would be an example of a remote online lab. I have given some other examples of online labs where you can do this. Labs Land is one that I learned about at my last IEEE Education Society session. There's also Georgia Tech Robotarium, where you can log on and drive their robots around. And you can also remotely control a VM rover as well. So all of those are examples of where you could log on virtually and interact with an actual object. So the great thing about robots, as I've already alluded to, is that it is multidisciplinary. So no matter where you're coming into this field from, there's something about a robot that you can connect with. A robot is a machine. It is a mechanical machine with gears and motors that has electronics such as sensors and a controller and software in order to give the robot intelligence. And then there is going to be some type of interaction with a human. You're thinking about bias and artificial intelligence, bias in AI, et cetera, and things like that. So there has to be something about the human aspect of it as well. So because of that, that's why I say robotics is ideal for STEM and STEAM, because sometimes the arts part of it is humanities or ethics, or how does it interact with a human in a way that feels safe, et cetera. So that's why I like robotics, because I can do so many things with it. So here's my first interactive chat question. On a scale of 1 to 5, with 1 being I know nothing about robots and 5 meaning I know lots about robots, put a number in the chat between 1 and 5. 1, I don't know much about robots. 5, I know a lot about robots. I want to see where the numbers are, because this kind of scales the way that I do my presentation. 1, I know nothing. 5, I know a lot. I see a 2, 3, 5, 5, 1, 2, 3. I see a lot in the middle. 3, 3. I see threes. Okay, so it looks like people are kind of in the middle. I mentioned 3.5. I do presentations for children and adults, and I use some of the same slides. So the level of detail I go into is closely related to how much I think you know. So what is a robot? Simply put, a robot is a machine. It is a machine that is given intelligence through software. You know Rosie from the Jetsons? Yes, Rosie was the first robot I knew as well, which is why I have Rosie on my slide. So it is a robot that is given machine intelligence through software, where the amount of intelligence may be based upon the number of sensors or the diversity of the sensors. Yes, Lost in Space was another big, very popular robot when I was growing up. So, so it's autonomous. Autonomous is how much can a robot do by itself? If the robot does not need human intervention at all, then it's fully autonomous. That means it does not need help at all. If it's a remote control robot, which means you have to drive it and give it to perception, it's teleoperated and it's not autonomous. Most robots are semi-autonomous, which means some things it's programmed to do on its own. But sometimes if there's a perception issue, which means it cannot figure out where it is or what something is, or if it gets stuck, the human may have to step in to help it. A robot has a body. It's very important to state that a robot has a body, because there are things called web bots now. A web bot is a different kind of bot that basically scours the internet and looks for information. So the types of robots we're talking about have a body that is designed based upon what the robot will do. If the robot is going to vacuum your floor, it may be a little disc on the floor. If it is a drone, it may have propellers that fly over a stadium, etc. A robot also will have sensors. The robot will have sensors based upon the task that it has to complete. So it may have sensors that color sensing. It may have temperature sensors. It may have sonar or infrared sensors. So the sensors on the robot give it its intelligence as well, and you select the sensors for a robot based upon what the robot has to do. Once the robot is given a task, it acts on the world. It acts on the world by using its effectors. The effectors may be propellers, grippers, wheels, tracks, any of those. And it acts based upon actuators. The actuators could be motors, hydraulics, vacuum tubes, or any of those things. And of course, the robot should have some goal. It's not really a robot if it doesn't have anything to do. It's a paperweight, so you have to give the robot something to do. A robot is made of a brain, a controller. That could be Raspberry Pi, Raspberry Pi Pico, Arduino Uno, lots, crickets, microbits. I use lots of brains on my robots, Linux, ROS, whatever. Software inside the brain is how the robot does things. It has the body, as we talked about already, the actuators and the effectors. Robots are ideal for 3 types of tasks. It's called the 3 Ds of robotics. Tasks that are dull, dirty, and dangerous. Dull, dirty, and dangerous. Dull task, a manufacturing facility, an industrial manipulator, a robot that is picking up a car door and sticking it on a car all day. That is something that if a human had to do it, one, would not be safe, and it would become dull because they would do it all day and they would start possibly making mistakes and injuring themselves. Robots are also ideal for dirty tasks. I worked in a windshield manufacturing facility. There was a paint room. A paint room is not a place you want a human working all day because they would inhale those toxic fumes. So painting robots are an example of a dirty task, something you don't want a human to do all day. A dangerous task would be a bomb disposal robot, a robot that is looking for IEDs in the military. That's not something that would be safe for a human to do. Dull, dirty, and dangerous tasks. So as I mentioned earlier, there are levels of robot autonomy. Fully autonomous is very, very difficult to achieve. It is because there needs to be a diverse sensor suite, and the robot needs to be able to react to a lot of different circumstances. The main place where robots will typically need help is in sensor feedback and perception so that it understands what's going on in its world. A teleoperated robot fully is like a remote control car. A remote control car could be considered a robot, although it cannot do anything on its own. Guided control means the user tells the robot via points where to go next and what to do. Shared and traded control means that the robot and the human are like partners, and they share and trade control based upon being aware of what parts the robot can do well, what parts the human can do well. Supervisory control is where a human supervises the robot and only steps in when it sees that the robot has gotten into trouble, like it may have gotten stuck or it's not making progress towards a goal or a task. Teaming and collaborative robots, cobots are big right now. Cobots like the Baxter robot is an example. There's another cobot whose name I cannot think of right now. This would be robots that are like teammates and they actually work next to each other. In a Sawyer is another. Sawyer and Baxter robots would work next to each other in the manufacturing facility. I will leave time for questions at the end, but if you think of any burning questions right now, feel free to also put those in the chat. So artificial intelligence is an internal model of the world, and it's how you give the robot its levels of autonomy. It's a way for the robot to do problem solving, planning and reasoning, knowledge representation, and search. This image on the right is a screenshot from my dissertation. And it was the way that I gave artificial intelligence to my mobile robot and presented that knowledge back to a user in a human robot interface. So it presented the data from the robot's perspective. It's called a sensory egosphere. It senses the world where the robot's ego is at the center. In this example, it just was basically using sonar and infrared data. And in the middle, it was using color and camera to determine where objects were around it. So the user could see the robot's knowledge from the intuitive perspective of the robot. So robots use sensors to see the world, such as a microphone to hear, a sonar to see, or a touch sensor on a gripper or force feedback to determine when it has picked something up. So the 3 robot primitives that we use to develop artificial intelligence on a robot are sense, think, act, sometimes also called sense, plan, act, think. The most important thing is the sensor is integral to a robot's intelligence. If the robot cannot tell what's going on around it, it cannot make decisions independently. That's where I talked about the human has to help with perception. If the sensor cannot determine what's going on, the human may have to help the robot. This is the reason we also have sensor fusion and sensor fashion, because if I need to find a red ball, an infrared or sonar sensor may tell me there's something there. A camera may tell me that the object is round. It may also help with distance, but I may also need a color sensor to determine whether it was a red or blue ball. So different types of sensors come together to give you more information. That's why I say a robot's intelligence is based upon the number and diversity of the sensors that it has. Based upon that sensor feedback, the robot then comes up with a plan to make a decision about what to do next. And then it executes that plan on the world. That's called sense, think, act. So mobile robot control, once you have the sensor data, can either be global or local. Global control would be a robot that localizes, figures out where it is in the world, builds a map of the world, uses a position in the world to plan a path or follow a path. Local on the robot is sensing and perception, like I said, sensing the world, using that raw data to get information. In other words, I've sensed something about the world and I know I'm next to a wall and I want to follow the wall. I've sensed something about a world. I saw a red ball and I want to push the red ball into the corner. That's where it takes that data and uses it to make a decision based upon the real world information. And then the action occurs where it either acts on that task or it executes. So once again, the perception is an integral part of everything it does. A robot is in the real world or a simulated world like I use with my students. It makes a perception or an environmental model. It figures out where it is in the world. It comes up with some kind of cognition of what it wants to do, and then it moves. There are different kinds of robot control architecture. Classical AI, or artificial intelligence, is called deliberative control. Deliberative control. Okay, that's what that top one is. Modern AI is called behavior-based control. Behavior-based control. So for that top one, the robot senses, plans, and acts in a linear fashion. That is a slow method of robot control because once the robot senses, plans, and acts, most likely the sensor data has changed. That's why people moved away from sensor-based classical AI to modern AI, which is reactive control or behavior-based control, because the robot is constantly sensing, constantly getting feedback. That first method is called an eyes closed method. For example, the robot detects a ball, it goes through the whole plan, and then it begins to act on the ball. The ball's now no longer there. Or it detected a person, and then by the time it started to execute the task, the person had walked away. So that's why the more attractive, or the one you see developed in the 80s called modern AI, is more acceptable because all of those behaviors are running in parallel. And if the sensor data changes, the robot can act in more real time. The negative about that second one is there's no planning. There's just sensing and acting. So there's now another kind of control called hybrid control, behavior-based control, where some things are done at the planning level and some things are done at the reactive level. So here is an example of how you would give feedback to your robot. It's called feedback control. Feedback control. Open loop control for a robot to follow a wall would mean it detects the wall and it just starts driving. If it never measures again, if it's hitting the wall, it has no idea. It doesn't adjust, and it probably is not going to follow the wall for very long. What you would want to do is add a sensor. So my robot follows the wall, and proportional to how close it is, the robot turns left, turns right, stops, etc. And it is constantly polling sensors to determine where it is. We do this with a microcontroller. So the robot takes the sensor data, measured in terms of voltage, converts that to a distance, and then it uses that with proportional PI or PD control to determine where it is, okay? Here's an example of what that looks like. I have a robot that is going to follow the center of a hallway. Proportional control has a lot of oscillations. It may get down the hall, but it won't be very centered. Then PD control, it'll be centered, but it has oscillations. So that is now, you're at the integral control, and that gets rid of the steady state error. This is called reset and rate control, reset and rate control. The derivative control resolves the rate stops the oscillation. Reset, the integral control, corrects for steady state error, okay? I'm hoping, I did not ask for everyone's level, but I'm hoping I'm not giving too much detail about the controls that you're completely lost, but hopefully it makes a little bit of a sense to you. So once again, proportional control means the robot takes an error based upon where it wants to be and where it is, a gain on that error, sends that out to the robot, and then you can determine how to reduce it to 0 so that if I want the robot to follow down the center of a hallway, it's able to do that. Okay, so here's another example of proportional movement where I want to move the robot a certain amount forward, and I use an encoder. An encoder counts robot wheel turns or clicks, and it determines how close it's gotten. And so based upon where it thinks the robot is, how close it is, the robot will adjust in order to move at a certain distance. Another way of illustrating this exact same concept is with a flow chart. I had mentioned earlier that I have my students present their software design plans in different methods, whatever they're most comfortable with. So here will be another way of determining how far a robot moves based on a counter where you want it to slow down proportional to how close it is to stopping. We know you need to decelerate, otherwise the momentum will carry you past the stop point. So here's a way that you could do that with a counter. Yes, diagrams are great. I'm a visual learner as well. That's why I show lots of images and videos. So once again, here's another one where the robot has to move away from something by 10 inches, kind of like wall following, except this is obstacle avoidance, where it's trying to move back to keep from hitting something. And here's what that would look like as well, where if the robot is within 2.5 inches of an object, it moves away at 100% because it's really close. If it is less than 5 inches, it starts to slow down so that once it gets to 10 inches, it moves slowly and then it stops. So it's just the opposite of the other one. The other one was moving forward at a distance. This one is moving away from an object at a distance. Here's a video of using a feedback controller in order to have a robot react. So it's sensing, planning based upon the IR remote in my hand, and then making an action.
So hey, saints and lovers of STEM, now that I am packed, I'm going to be gifting this robot. Tuned and come back. Infrared receiver, and we're going to walk. Here we have our infrared remote, and then here we have our infrared receiver. And we're going to walk through the things that the robot does, and then we're going to show how to wire it up and write the program. So the power button makes the robot spin. Then we have a volume button, makes the robot move forward. We have a button that makes the robot spin the other direction. Then we have a button to make the robot go forward. The robot sing and dance. We have another robot to make the robot turn. Let's move it back because we don't want little buddy to drive off the table.
So that is an example of sensing, planning, acting. The infrared receiver on the robot is the sensor. I have written the plan out in my code, and when I push the button, the action happens because of my code. Okay, here's another example of this with a light sensor. This robot has a photoresistor on it, and that resistance changes proportional to incident light. And I have written the code to have the robot to act out some type of behavior based upon how much light it sees. You can use this to make a robot that is in love with light or light tracking. These are called Bratenberg vehicles. So it either moves towards the light, it moves away from the light, it runs towards the light, etc.
Hi. Resistor. Here's our 10 kilo ohm resistor. So here we have the photoresistor that is tied to the 5 volts, and we have the 10 kilo ohm resistor that's tied to ground. And then it's kind of hard to see, but we have a blue wire here that goes over to A0. So here we have our light tracking code, and I will only highlight the new parts that we will use for this. So first we have the LEDs that robot should stop moving. That's the light that will come from our flashlight on our cell phone. Then in our setup function, ambient light, we read robots.
Since we're going to do a little bit of robot work today, I'm going to skip the code because we could talk about that when we get to that point. So I just wanted you to see the robot.
Like on the robot. So first you're going to turn the robot on. And what you'll see is that it immediately starts going at top speed because it's seeking out more light. So when it gets enough light, it stops, which shows love of light. And then if the light starts to dim, it starts moving back because it wants more light. The darker it gets, the faster the robot goes. So once again, the more light I bring, eventually when it's basking in the light or love of light, the robot stops. But as I take the light away, the robot starts moving.
That's an example of proportional control. The robot's motors are proportional to the amount of light that the robot sees. Okay. So another way of showing robot behaviors is called subsumption architecture or a state machine. A subsumption architecture is layers of robot movement where they subsume or inhibit the other layers by what's going on. This bottom layer is called obstacle avoidance, which means the first priority is for the robot to move safely in the world and not hit anything. Then if there is light and there's no object in the world, the robot should try to either move toward the light, move away from the light, or be at the light. So the actions are turn and forward. The sensings are move to the light and run away. And these layers happen interactively where they turn on and off based upon if I see light, if there's an obstacle, the object is obviously more important to get away from the obstacle and then to track the light. So my students also make these kind of software design plans so that when I'm grading their work, I can see what code they wrote and what it should do. And then this table down here explains in more detail. The light triggers the photophilic behavior, and that triggers the motor schemas to move to the light. There's a perception of the light and as well as the brightness of the light. So these would be functions in their code that they now call based upon whether there's a distance to an object or a distance to a light. And then when they demo it to me, I can see that it works correctly. So this same type of behavior can also be written in a finite state machine like this, where now you use the inputs to move from one state to the next. This is an example of a robot that is traveling between classrooms in a building. The robot starts on its journey and it's trying to get to a class. So it's going to continue on that journey until it reaches the class. Once it reaches the class, it's going to stop and stay in that state. Or if it never reaches a class, it gets into an error state and it gets lost. So this type of behavior, you would need some kind of coordinator in order to know if it's moving towards the class or if it's avoiding objects or students, or if it needs to stay right on the hallway in order to get where it wants. You would then write this as either a if condition or a switch case inside of your code that coordinates these behaviors and then turns each of them on and off with input from either a sensor or another behavior. Okay, I am to the point now where I am ready for some feedback. Like I said earlier, I'm not sure this link still works because I believe that the Jamboard went down. And if so, I'm going to have you put your feedback in the chat and we're just going to download the chat. But hold on, let me try the link first. And if the link no longer works, then we'll do the Jamboard. Actually, it looks like it's still up. So I'm about to paste this in the chat and I want you all to take a couple of minutes and go in and answer the question. Now that I've given you some high-level descriptions of robots, how do you think you could use robots in an online lab? You should be able to go in here and make a stick-it note and add your thoughts. Notice that we've had some stick-it notes in here before. I'm trying to find the stick-it notes. Okay, so it looks like they're getting rid of this on December 31st now. Where are the stick-it notes? I don't see the stick-it notes anymore. What happened to the stick-it notes? Oh, it's under view only. Why is that? Hold on one second. Let me see if I can figure out why it changed to view only all of a sudden. Anyone with the link should be able to edit. Let me try this again. I'm going to put it in the chat. And I'm going to refresh this. I don't know why it's saying view only. Huh. All right, we may have to end up using the chat. You can view this document to make changes, ask the owner for edit access. I am the owner. Maybe it was under a different one of my accounts. Hold on one second, please. I have multiple Google accounts, so I have to see why I am not able to.
I think they're getting ready to retire it, and they're giving you till December 31st
You think
to
that's
download
why?
whatever you have.
But they won't let you put anything on it anymore. I think you're right. Okay, everyone, please put your ideas in the chat. Always taking away our favorite tools. Yes. Please put any ideas you have in the chat, and I will download the chat at the end of today's session. You're right. I thought that December 31st meant I could use it to December 31st, but yeah, I think you're right. I think they won't let you use it anymore. That's horrible because I've checked all of my accounts and it's not active on any of them. Yeah, every account is view only. Just put your ideas in the chat and I'll take a look at it later because I want to use that feedback for my final report. Yeah, they won't let you put stuff in here anymore, I guess. Oh, well, we tried. It was a really cool idea while it lasted. Okay, there you go. All right, so once again, the question is, how could you use robots in online labs? How could you use robots in online labs? Okay, gesture control robots, yes. All right, I'll give you a couple of seconds to do that, and then I will go back to the presentation. Once I see the chat start to slow down, I'll move on to the next topic. All right, so let's do a little feedback since we're here waiting anyway. On a scale of 1 to 5, thinking about your level of understanding of my presentation while people are putting in their thoughts. Well, let's do 1 to 5 again. 1 is I'm completely lost and I don't know what you're talking about, Professor Berry. Number 5 is I know all this already. I'm not being challenged today. Okay, I see a 2. Very good. And a 3. 3s. I see lots of 3s. Actually, 3 is hitting about on the right point. I think if you're 3, that's pretty good. 1, I need to do a better job. 5, I'm sorry. I can't give you more today. Go and look at my YouTube videos online. Okay, 3. Most people are 3. Amadou says can't be 5. Okay. And keep the ideas coming too. I love that. I'm going to get all the ideas out the chat at the end of today. Great. Sorry, Luis. I need to give you more. Okay. Okay. I am now going on to the next slide. So introducing my robot. So all of this is leading.
You asked about the applications, but we didn't see too many answers about how to use, what are people are expecting to use a robot for.
So somebody put control systems lab, 100%. I also teach controls. Automated sorting station. So that would be a lab as well. Agricultural plant inspection. That could be one, but you got to think about what sensors and what part of agriculture, like what are they using it for? So you'd have to think about what kind of sensors. I have done a project with a student before who they used one, they put soil sensors on it and environmental sensors. And then the farmer could remotely log into the system and determine things like, I need to water more, or the soil has gotten too acidic, things like that. So that's another application that you could use a robot for. Lots of programming classes use robots as well. Gesture controlled robots. You could add a, I can't think of what it's called. The thing with the Wii remote. You could add that kind of thing where or a camera and use gestures. We have a robot in my lab that we use gestures, and based upon the hand gestures, the robot is supposed to try to react with a happy face or sad face or things like that. So there are a few in here that are, but they would have to be fleshed out in order to get more detail out of it, Hamadou. But I do see a few people putting some ideas in here. The collaborating with a remote user. I'm going to be teaching a class in human robot interaction. The first level of that is, can you make a robot that can interact with a human on a laptop or a system, and then can you put the robot somewhere else remotely and have it do that? So we got a few examples in here, but please keep writing them. You don't have to stop because I'm moving on. Please keep writing them. I just want to be conscientious of your time and make sure we get to the point that you get to do some roboteering today. So that's where I'm trying to get to. So a great way to do this work is open source robots, which I call flower bots. Flower because they grow with the user, and infinite because there's an infinite amount of ways that you can obviously program the robot to work. They're low cost and open source because they are more about 50% 3D printed, and they provide access to communities that may be marginalized or minoritized or under-resourced in STEM with 3D printed files, CAD files, and the code online. Anyone, anywhere can make my robots. All of my stuff is open source. You don't have to buy a robot from me. You don't have to get the knowledge from me. You can go online, download my files, print your own robot, modify the files, change it to what you want. The robots are modular in order to be modified so that you can add your own controllers, sensors, peripherals. You can put a gripper on it. You can make it bigger or smaller. I've had people take my files and make them smaller. They said the robot was too big. Flexible enough to be appropriate for service, outreach, education, and research, and appropriate for everyone from novice to expert levels in robotics from K through 12, university, graduate, makers, professionals, and more. Here are just a few examples of my robot being used by college students for high school competitions. And then here's one in the middle.
This is how you build and program your robot.
These are high school kids. Their teacher downloaded my robot from TikTok.
First, we assembled the robot by watching a YouTube tutorial. Then we wired the robot. Then we created a code for the robot to perform. The most challenging part was wiring the robot. The most interesting part was coding the robot and watching it perform.
So robotics for the streets means I use social media actively to promote my work. And I have had people who found my robots on TikTok and made them, Mastodon and made them, Twitter, Instagram, you know, wherever. So that's a big part of robotics for the streets, is taking my robots out of my classroom and taking them where I can meet the people who I think would be awesome members of the STEM community, but may not have access to an engineering classroom and that technology. This is also why I put my materials on YouTube, Instructables, and everywhere where people can go to learn about these things. So Maria, these next two slides are because of your requests. So I made these last night for you. And you had asked me the differentiator between Lilybot, DaisyBot, and RosieBot. I mostly do Lilybot right now because there's been such a demand. I haven't had time to work on the other two yet, but we're still tweaking them. Lilybot was primarily designed for service for the novice learner, K through 12. And right now it is able to work with a microbit, Arduino Uno, Raspberry Pi Pico W, Circle Playground Express, and we have used it for service and education for children and adults. DaisyBot would be more for an intermediate learner. It's a larger robot, so it would be for also K through 12 or university. We have had it working with an Arduino Mega. In that previous video you saw, it was used in a competition where the students used a PlayStation controller to drive the robot around. It could also have a Raspberry Pi or a Pico W, and it could obviously be used for service, education, and research. Thank you, Harry. Keep them coming. And RosieBot would be the more expert. Sorry, that is a typo. Typos drive me crazy. That would be more for a more expert learner, right? We have had a person put a camera on the robot and then use that to do reconnaissance, where they had their cell phone attached to the robot wirelessly, and they were able to send the robot into a building and look at where the robot was exploring. It could also be a Mega, a Raspberry Pi, and that would be more for education and research. I would probably think of this one probably more grad student level, actually, but it's your choice, obviously. So learning objectives for each at the most basic level, which is what we're going over today, would be defining a robot, the parts of the robot, comparing and contrasting various sensors, explain how tasks work on a robot, What are the robot primitives? How do you use those to make artificial intelligence on the robot? And creating basic electronic behaviors on the robot. This is what we're doing today, okay? The next level up would be my robotics class that I teach my undergraduate students. This is where we go into more detail about robot control architectures, feedback control, looking at advanced behaviors based upon feedback control and control architectures, implementing mapping, localization, path planning, and path following on a robot. Rosie would be taking the robot beyond classroom concepts and now looking more at research-based concepts like human-robot interaction, collaborative teaming between robots, swarming, flocking, things like that, and using computer vision for navigation, path planning, mapping, etc. So Maria, those 2 slides are for you. That answers the question that I told you I was going to put in the slide. Okay, so some of the resources that are available for these robots, because they're open source, TikTok, Instagram, Twitter. There's projects on Instructables, Hackster.io, code and CAD files and videos. And because I expect them to be used for people of various levels, I have examples of graphical and text-based programming.
In order to use CodeKit in order to program short-range infrared sensors on our LilyBot, we're going to create 2 functions. The first function is getDistance, which will read the analog pin A0 where the IR sensor is connected. It will then convert that value into a voltage. And then once it converts,
I'll turn up the volume. I saw somebody said turn the volume up. Let me see.
For the short range sensor by making that value distance equal to 29.988 times the voltage raised to negative 1.173. Then to convert that from centimeters to inches, divide by 2.54, and then return the distance. Our other function is just turning all the LEDs off because the LEDs are used to represent the distance to an object. So next we program the setup function by attaching our yellow, red, blue, and green LEDs to pins 10, 11, 12, and 13. Then in the loop forever function, we use if conditions. So if our distance is less than 4, we turn on the yellow LED. If our distance is less than 6, we turn on the red LED. If our distance is less than blue, we turn on, if the distance is less than 8, we turn on the blue LED. And anything greater than that, we turn on the green LED. Then we wait 0.1 seconds, turn all the LEDs off, wait 0.1 seconds, and then we loop through again. Let's take a look at what the Arduino sketch code looks like for this code. So finally, here's the code generated in CodeKit using our graphical programming. First, we declare our integers, yellow LED, red, blue, and green LEDs, our floats for value, distance, and volts, which are for the IR sensor reading. Then we have
this is what I do with younger kids. I do graphical programming, and then as they're getting older and more comfortable, I show them how that graphical programming gets translated into text-based coding. You can do this with Arduino Uno. You can do it in Python. You can do it in JavaScript for MakeCode when I do microbits and Circuit Playground Express. So they're now learning how those puzzle pieces become code. And then finally, of course, I show them how this code translates to the robot, which is next.
Turns on. Let's take a look and see what this looks like on the robot. Okay, this is a demonstration of our IR sensor test. This is our 2Y0A21 IR sensor. So you see when there's nothing detected, it's green. So if I put my hand close, it turns to red. And as I move my hand back 10 inches, 8 inches, 6 inches, and 4 inches, the color will change. So as I move back and the IR sensor detects the next color, it changes to yellow. And if I continue to move my hand back, it changes to blue, and then eventually green when nothing is detected. Here's our front IR sensor, and green when nothing is detected, red when my hand is really close. As my hand moves back, it changes from red to yellow. And if my hand moves back more, it changes to blue. And eventually, if I change back far enough, or if I remove, it's green. So this is proof that our IR sensors are working, and they can also be used for obstacle avoidance, just like the sonar.
Okay. I'm putting a few links in the chat too. I think some of them are at the end of the presentation, but I'm not totally sure. So I'm putting them in the chat as well. And here is an example of where I did the same workshop for engineering professors so that they can then go into their community or go back to their school and use these robots to teach their kiddos.
Even educational robotics can be very expensive, $200 to $300. Robotics competitions can be in the thousands for kids to participate. So if you're from an under-resourced area, it's very difficult to get involved. And even if we get past the cost, sometimes there's a knowledge barrier. You just may not have teachers or adults in your area who know enough about electronics, mechanics, and software to be able to help you with robotics projects. I have created an open source robot that is mostly 3D printed, which means it's low cost. And because it's open source, that means it takes care of the access problem where anyone who can get to the internet and can get to YouTube can look at how to make their own robot, print it, and program it. So I came up with this idea because it was a way to get teachers and communities like Girl Scouts, Boy Scouts, and things like that into robotics without them having to break the bank. What they're going to learn today is how the 3D printed robot was made, as well as how to convert it as your skill level improves. So we're going to start with graphical programming, like making your Blockly by using make microbits, and then we're going to move on to Arduino Uno, which is text-based. So as we're changing the controller on the robot, it's going from K through 12 elementary to college level, university level, and maybe even graduate school, so that one robot is growing with you as your skills improve. No matter what your area is, because robotics is multidisciplinary, you will now be able to use that whether you are in computer science, mechanical engineering, electrical engineering, social psychology, human-robot interaction. You can use it to touch on your field in order to teach people more about artificial intelligence and about what you want them to know just by using that same robot.
All righty. Sorry, moving on. So now I am getting into the part where we're going to be workshopping some. So I know some of you got robots, some of you are just here to learn, and that's perfectly fine. Those of you who received one of my robots in the mail, let me see how I can ask this in a way that makes it quick. Maybe we're going to do numbers again. One is, I did not build my robot. 2 is my robot is partially built. 3 is my robot is fully built. 1, if you got a robot from me, it is built. 5, what does 5 mean? Super built. Maria's is super built. That means super built. No, I'm kidding. 3. Okay, looks like I'm getting mostly 3. So everyone built their robot. Okay, that is great. All right. Here's my next question. I'm getting all 3s. All right, David still needs to get his robot built. Okay. If you built your robot, next question. 1, I have done no programming on the robot. 2, I've done a little programming on the robot. 3, I've done a lot of programming on the robot. 3, a lot of programming on the robot. That's great. 2, some programming on the robot. 1, no programming on the robot. I just built it. All right, I see a 2 and a 3. Okay, 3. Okay, good. All right, so that means I will go over high level how you put the robot together, because it looks like most of you did build your robot. So I'm basically talking to the people who have not had time to build their robot yet. Okay. And I also put one more link in the chat. That was the last one for David. I now think I have every link that David needs. Okay, now, so the parts of the robot, it's 3D printed. Like I said, everything that's not electronic. So the holes are what makes the robot modular. So depending upon what controller I put on the top, I put a battery pack on the bottom in order to give that power. So if it's a microbit, it could have a 9-volt battery pack. It could have a 4 AA battery pack or battery module. I then have a mount for a Raspberry Pi Pico W. I have a mount for an Arduino Uno. I may have a different battery pack. Same motors, same wheels. As long as it's a Lilybot, the chassis is the same. But if you really do exhaust everything you could possibly do with a microbit and a motor bit, you can always just swap out the controller and keep the robot. So this is the flexibility in the design in order to continue to grow with the robot, thus the name Flower. Okay. And here is what the Arduino Uno looks like that you have built. I think I sent most everyone a 9-volt battery pack. You could also do the same thing and use a 4 AA battery pack, but I think I sent everyone the 9-volt battery pack. The motor controller. There are different kinds of motor controllers. There is a SparkFun Redboard motor controller here. There's a TB6612 motor controller, which I believe is the one that everyone got. And then you just start adding things to your robot and programming. So this is called an embedded system. An embedded system basically is a robot. It takes data from the world, then it performs some actions, and then it outputs that data. So your Arduino Uno is what creates our embedded system, which is now the brain of our robot. So an Arduino Uno is probably the most basic Arduino that most people have. It's a great platform for first learning microcontrollers. I use Arduino in my classes because there's so much online material on Arduino that even if you don't have me, you should be able to get online and find resources that you need. There's 14 digital I/O. There's a pulse width modulation output, which is basically how you would play a buzzer or something that requires frequency or analog data, as opposed to digital, which are ones and zeros or on and off. And you have a power jack and a reset button. So it's an embedded system that takes in data from the world and outputs data, in this case, to our robot, and it uses general purpose input and output in order to get sensor data or to send output to like a buzzer or to an LED or to a gripper. Like I said, digital data are ones and zeros. It's like a light switch that you turn on or off. Analog data is data that is anything along a real number line. An example of an analog sensor would be a sonar sensor or an infrared sensor. It can take any number between 0 and 5 volts proportional to distance. An example of an analog output I just told you would be a photoresistor. I'm sorry, a buzzer. A buzzer. A photoresistor is an analog input. A potentiometer is an analog input. A digital input is a what? I'm starting to get tired of talking, which means I'm doing like I do in class. I'm asking you a question in the chat. What's an example of a digital input? Something that the robot should be detecting was on or off. Digital input. Digital input. I got nothing. Where's my 5? Power, on and off. A button. A button. An LED is a digital output. Very good. A button is a digital input. An LED is a digital output. A line following sensor that is looking for infrared on and off. A proximity sensor. A proximity sensor, either on or off. LED is a digital output. Very good. LED. First one we always talk about. The LED circuit is the hello world of electronics. In software, you normally print hello world to a serial monitor as the first task you complete when you learn how to code in a language. For electronics, it's getting an LED to turn on, and that's what we're doing today. That's the first thing we're going to do today. To get an LED to turn on, you can wire it on something called a breadboard, and they used to actually put electronics on breadboards. That's where the name came from, where you have a battery, a switch, and the LED, and a resistor in series with it. You put the resistor in series with the LED because you don't want to burn the LED up, and that limits the current and drops voltage across the resistor. We use breadboards that look like this now. It's also called a proto board. And if you pull it apart, it has metal tabs underneath. And those metal tabs are used to make connections between the electronic components. That's called a node. The meeting point of the components is called a node. And when I make them connect, like these wires and metal tabs are doing, I can turn the LED on. It's coming. The obstacle detection, your sonar sensor, it's coming. If I don't get there today, you can watch the video, but I'm going to try to get you to obstacle avoidance before I log off today, Abdul. That's my goal. So the breadboard is connected, and this one at the top is the breadboard on your robot. Every row is a different node. So if I want 2 elements to touch, I put their legs in the same yellow row. So if you think about these as letters, A through E, F through J, A through E would be one node, F through J would be one node. Then if you think of the coming down the side as numbers, 1 and 2 are different nodes, okay? Just like A through E and F through J are different nodes. So when I tell you to put something on your breadboard so that it touches something else, they have to be in the same row. Resistor color code. If I emailed you a kit, all your resistors are probably in the 100 ohm range, which means they can be used for your LED, 100 ohms, 200 ohms, 300 ohms, etc., or a 10 kilo ohm. I sent you a 10 kilo ohm resistor. Do not put the 10 kilo ohm resistor in series with the LED. The LED will not turn on. It's too big of a voltage drop. You have to use the 100 ohm resistors for the LED. The 10 kilo ohm resistor is for the photoresistor or the potentiometer. Photoresistor or potentiometer is 10 kilo ohms, which means a 10 kilo ohm resistor in series with it will be a proportional drop in order to read that data. If you mix the resistor up, you'll know immediately because it won't work right. Okay. So this color code tells you, you don't have that many resistors, so you probably don't need the color code anyway. But for my students, I tell them black bears run over yellow grass, but violet gently walks, because after you do a couple of hundred resistors, you really want to just have a color code. Go see now. I left off of here. Go see now. Gold, silver, none represents the tolerance. These numbers represent the first number, the second number, and the multiplier. So that if you got a orange, brown resistor from me, that was 330 ohms, okay? So what you're going to do is you're going to put an LED in series with the resistor, and instead of a battery, your microcontroller is going to turn on the resistor, the LED. So you're going to put an LED in series with a resistor. Anode is the long leg. Cathode is the short leg. If you put an LED in backwards, it will not turn on. Current has to flow one direction. The ground connection has a flat rim on the cap of the LED as well. So that we've talked about, you can have analog data, digital data, or mixed data. You can actually do analog or digital on an LED. Analog data controls the brightness of an LED. Digital turns the LED on or off, okay? So these are some SparkFun images that I use because they're easy. I need a bright flashlight to read the resistor codes. Now with my old eyes, I know, Mark, I'm sorry. I do too. I have a big magnifying glass that I use. So here is an example of connecting LEDs to buttons and a resistor. So this is now using a digital input to turn an LED on. So you're seeing digital input and digital output at the same time. I'm not explaining these circuit diagrams too much because I don't know how many of you guys are electrical engineers, and I'm trying not to overwhelm you with too much technical stuff. But over here, these diagrams are basically what you would build on here. So there's a symbol for an LED, there's a symbol for a resistor, and then pin 13, pin 3, and pin 2 would then be microcontroller connections. And then up here are the resistors. So here are pull-up 10K resistors for a button. You don't have to do this because there's an internal pull-up on a microcontroller. And then the 330 ohm resistor for the LED. All right, here's an example of programming an LED. If you did the LED already, put that in the chat and let me know. People who got a robot, let me know if you've done LEDs in the chat. All right, I see a lot of dones and yeses, so I'm moving on. Remember, you are dictating the pace at which I present. If I'm seeing you've done it, I'm moving on. So the way that I do this for people who've never done this before is I use Tinkercad. So here's an example of using Tinkercad to get an LED working on your robot, where we do it first without the microcontroller. We do it with a battery. And since you did this, I'll just speed through it. But basically, oh, come on. Then it would go through the cathode to ground. Let me show you what happens if I don't put the button in. I take this wire and connect it directly there. And I press start simulation. The LED turns on. Ooh, it's magic. Y'all ain't no fun. All right, but I don't want to do that. I want to show you how to use a digital input. So I'm going to take that out. Did everybody understand what I just did there? I closed the circuit so that the current flowed from voltage through the LED to ground.
All right, this is why you never touch voltage power lines, because you have a resistance and the current would flow through your body to get through lower resistance to get to the other end, and it could shock and stop your heart. And that's how people get electrocuted when they get touched by a power line. Full of fun facts. Okay, so I'm taking this away. I'm rotating my button so that I can put it over the ditch. Remember, you have to put things over the ditch so you don't short it out. So I got to put the button there. All right, it doesn't work otherwise.
Put in the chat if you got the button working on your robot. Put in the chat if you got a button working on your robot.
So now I'm going to put a wire that goes to one side of my button. And you tell me, where does the other side of the button need to go? Okay. And then I'm going to start my simulation. Why did nothing happen? The light didn't turn on. What's going on? Is it broke?
Yeah.
I didn't press the button, right? The current's not flowing because I have an open circuit. My pipe is broken. I have to close the pipe so that the current flows. So, why didn't it work? Oh, there it is. I wasn't pressing the button, sorry. So if I press the button.
All right. You may not could have heard, you maybe could not hear me over the video. How many of you got buttons working? I'm moving on if you got buttons working. Did you get buttons working on your robot? Yes, I see a yes, yes, yes. Buttons turning LEDs on and off on your robot. Where can we find the free simulator? The one that I just showed you? Okay, that's called Tinkercad. Let me put it in the chat. This is the one that I told you that I have my students simulate stuff on sometimes. And it is absolutely free. I'm about to put it in the chat. Okay. It's called tinkercad.com. There is also another one that you can use with kiddos to simulate robots. There's a couple others. I'll put that in the chat as well if any of you do stuff with kiddos. This is another one that simulates robots when you write code. And the other one is scratch.org, I think, simulates robots as well. I think. So any of those work for that. Okay. All right, let's keep going. We're trying to get to, somebody asked me about the obstacle avoidance. So I'm trying to get there. We have about 1 hour left. I'm trying to get to the obstacle avoidance. Okay, but I have to make sure you understand the basics of wiring as well as digital and analog. Okay, so the potentiometer, you got one of those in your kit. That is an analog input. You can use that to control blink rate or intensity of an LED. You could also make an LED dimmer circuit. Here is an example of the potentiometer working. I won't show the whole video. Uh-oh, that one went to the internet for some reason. I don't know why it did that. So what you see here is when I turn the potentiometer, the brightness of the LED gets dimmer and brighter. Uh-oh, it doesn't like this one for some reason. I don't have a resistor in here. The potentiometer was my resistor. So what you should have seen there is that at the end, the LED actually burned up. It broke because the potentiometer is my series resistor instead of the actual resistor of 330 ohm. So if I turn the potentiometer too far and it goes to 0, there was too much current and the LED burned. Okay. So things you're going to have to learn to do in Sketch, which is like C+ code, is writing functions to call, like you're going to need a function for get distance to read the sonar sensor. You may need for loops in order to run some code continuously, but a microcontroller also just has a loop that runs code continuously. Sometimes you may use an array. Like if I have multiple LEDs I want to control, I will use an array to do that. The setup function in the microcontroller is for code you only want to run once, and code you want to run continuously, you do a loop for, and digital write turns things on and off. There's also an analog write for sending out analog data. And there's an analog read and digital read, okay? You also have if-else conditions to determine if a sensor or something, it reads a certain condition, and then based upon that condition, you execute something. This is what I said when I do state machines on my robot. I use either if-else conditions or I use switch cases to determine what behavior to execute based upon sensor data. You also may use Boolean logic. Boolean logic is ands and ors. If the robot is in a corner and it sees a certain color, something should happen. Both things have to be true. Or if the robot is in a color, in a corner, or if the robot sees light, if either one of those situations happen, the robot backs up. That's a way for you to look at multiple conditions to determine when a robot takes an action. So it's another way of making decisions. Here's an example of having multiple buttons on your robot where depending on which button is pressed, a different thing happens. This is kind of like that infrared remote example I showed you where different buttons on the remote made different things happen on the robot. Okay. So like I said, it's used to check multiple conditions. So here's now, instead of one button, I'm saying when two buttons are pressed, I want something to happen, or when two buttons are released, I want something to happen. I'm now using and or conditions in order to execute something on my robot. And you saw in one video that I had a photoresistor, and you put a 10 kilo ohm resistor in series with the photoresistor, and then when it detects light, the robot should change, okay? So now I have my microcontroller connected instead of just having that 9-volt battery, and I am just using my setup function to read the code. I hate it keeps going here. I don't know why it's doing this. So I have my code, and when I now run it in the simulator, what it does is it's going to blink the LED. So not a button press, not a 9-volt battery. It's now getting the power from your USB cord connected to your computer to the microcontroller. Or from your battery pack to the microcontroller. And if I change the delay, what you're going to see is that the LED blinks either faster or slower. Okay. Let's go back to the slides. Okay. I won't do the fade code, but very similarly, you can use inputs to make that happen. Okay, I want to get to the point where we're now ready to do something on the robot. These slides are available to you. So for all the ones that I'm skipping over, feel free to go in whenever you would like and use them, okay? So I have some example code inside of Tinkercad. I'm going to skip to the ones for the robot, but if you want to step back and do any of these others, you can. So what you're going to see is in Tinkercad, I have one for the LEDs. I have one to play music on the robot. I have one to read the sonar and the photoresistor, etc. But I want to get us to one where we get the robot moving and get the obstacle avoidance going. So that's why I'm going to skip ahead. But you could go to any of these if you like, okay? And I'll put this, what you do in here. You go to tinkercad.com/join class. And the code to join the class is TKXUSPWA6. I made, in case you don't have a Tinkercad account, if you have a Tinkercad account, you can just log into your account. If you do not, you're going to need a nickname. And so I just made all the nicknames robot and some number from 1 to 100. So that's how you would get in Tinkercad in order to try some of this code on your robot. But I'm going to skip ahead because I want to get to one where we get the robot moving, okay? So, but what you see here is you take your Tinkercad code, you copy it out of Tinkercad, you go into arduino.cc, which is your cloud editor, you paste it in there, and you download it to your robot. This is not the only way that you can program a robot. You can also program the robot by using thani.org and also platformio.org. Okay, those are probably other options. There are lots of websites that you can use to program the robot. I pretty much stick with Arduino for beginners because it works. And it has an online cloud editor, okay? So here is an example where I'm running the code from Tinkercad on the actual robot. I wrote it in Tinkercad and then used Arduino and downloaded it to the robot. So I wrote just some blinking code for LEDs, and then I put that code on my robot. So these are running the same code. So the ultrasonic distance sensor uses sound to detect the distance to an object. It uses time of flight and sound to calculate how far. It sends out a ping and it listens for the echo. And based upon the time it takes for the echo to come back, it determines that there was an object 5 inches, 10 inches, 12 inches away. When I teach this topic to children, I tell them this is called echolocation, and that there are 3 animals in the world that also use echolocation, like sonar on a robot, to communicate with each other. 2 are in the water, 1 is in the air. What are they? Type it in the chat. This is how I'm waking you up. I'm asking you a question. There are 3 animals in the world that use echolocation, like a robot uses sonar to communicate in the world. Whales and bats are great. I haven't, dolphins, Maria gave it to me. I was about to say, I haven't seen the 3rd one. Dolphins, very good. Dolphins, whales, and bats. So if you're going to be doing anything with kids, that's a great kid question. Porpoise, I didn't know porpoise. I may have to look up porpoise. Porpoise and shark, I didn't know about those 2. I got to look those up. Okay. So we're ready to build the sonar circuit. Build the sonar circuit. I'm getting you to the point that somebody requested in the chat. How many of you have your sonar circuit built already? If not, this is where you should be right now. We are building the sonar circuit. What I want you to see here is before we connect the motors, we want to make sure you have the sonar working. So you are going to connect the trigger and echo pins of the sonar to pins 6 and 7 on your Arduino. You made it up, Maria. VCC goes to 5 volts. GND goes to ground. Okay, let's get your sonar sensor working. This is for, who asked me about the sonar sensor? Somebody in the chat asked me about the sonar sensor.
Aziz, Abdul Aziz.
Abdullah. Okay, so if you have not done this, you need to do this now because we're about to get the sonar and obstacle avoidance working. This is the last task we're going to do today because I'm assuming up to this point, you've gotten most of it done. You can also connect one LED. You don't have to connect all of them unless you want to, but I normally use a LED as a visual output that the sonar is working correctly. So if you have a sonar connected and you have an LED connected, then what you're going to do is as you move your hand, we should see the light turn on and off if the sonar is properly reading. Put in the chat if you have done this. Hi, 3 sisters from Niger. Tell me, are you wiring your sonar? Have you wired your sonar? Where's everybody at? So I'll know when to move on. You made a vacuum robot. Awesome. So you're going to wire your sonar, and then we're going to go to our Tinkercad code and walk through how you get the sonar to read, and then we're going to download that to your robot. That's what we're doing right now. Let me know if I'm going too fast, too slow, what you need me to do next, because I'm ready to move on whenever. I need some feedback, though, because otherwise I don't know what's going on. Is anybody wiring their sonar? How did you make we have it wired. Okay, thank you, Maria. How did you make the vacuum part as a real? How did you make the vacuum part of the robot? Yay! Those are your nieces? That's awesome, Hamadou. You have it wired up. Okay, I see a couple of people have the sonar wired already. That's 4 wires. And then, like I said, maybe just do 1 LED and then we don't have to wait so long. Maradi, Niger. Use it to avoid obstacles. The vacuum part is where I've never seen before. I don't know how you put the vacuum part. How'd you get the vacuum part working? Azariel. Okay, I'm going to move on because I don't know if anybody else is wiring. Okay. So you could also put a buzzer on your robot so that's another thing you can do to detect when the sonar has sensed something. If you put the buzzer on the robot and the buzzer goes pin 5 to ground, now when your hand is close, not only will a light turn on, but a buzzer will go off, right? We're going to do the code in a minute, but I just want to make sure you have enough stuff wired on it so that when we run the code, you can test that it's working. So if you did the buzzer, let me know. If you did the LED, let me know. If you did the sonar, let me know. The buzzer goes from pin 5 to ground, pin 5 to ground. Hopefully everyone should have enough wires to do this. The buzzer looks like a little black circle. I think the sonar probably looks the most like it does in real life. The buzzer looks like a black cylinder with a hole in the middle. Okay. Those who are building and wiring, how are you doing? We didn't use the buzzer, just the sonar with the LED for forward direction or backward. Okay. All right. Sounds good. They're making a suction chamber where the pressure difference is produced with the help of a DC motor and a blade made in 3D. Oh, cool. All right. Unfortunately. Oh, okay. All right. Everyone should have a chip in their kit. A chip in their kit. It's blue. Yours is not red like this. Yours is blue. The wiring's going to be a little different though, but I think I can help you with it. So let me try to do that. So some of the wiring is the same. So remember, when you put the chip in, it needs to straddle the ditch in the breadboard. So it needs to straddle the ditch so that one leg is on one side, the other leg's on the other. Like I said, your image may be a little bit different because you have a blue motor controller. It's TB6612. So some of the wires may be a little different. The main thing is make sure that pin 8 goes to AN1, pin 9 goes to AN2, pin 10 goes to PWMA. Okay. And also that pin 11 goes to PWMB, pin 12 goes to bin 12, and pin 13 goes to bin 1. Now, because your chip's a little bit different, you may not have this motor A01, A02. You're just going to have left motor to motor A, right motor to motor B. Yours may just say motor A, B, and motor AB or something like that. Unfortunately, my robot is downstairs, but so that may be the only difference. Is VN goes to VM, 5 volts goes to VCC, ground goes to ground, but your right motor is just going to go to where it says motor AB for one side. Left motor will go to where it says motor AB for the other side. You don't have a standby pin because that was a different controller, so you don't have to worry about standby either. So your main connections are 8, 9, 10, 11, 12, 13, and then VN 5 volts ground, and make sure the left and right motor get connected. I'm wondering if I have an image. I might have an image somewhere of your actual motor. Let me do a hunt and see if I have it somewhere. And please put a status update in the chat so that I'll know when to move on, okay? Thank you for coming, Cornelia. Watch the video later. Somebody has to leave, Hamadou. I am going to try to find an image of your actual chip if I can, maybe. let me know. Yes, you can have these PowerPoints. They're in the chat. There's a link to the PowerPoints in the chat. Hold on. Let me put it back in again. Let me find it. The link to the PowerPoint slides.
I put it on. Go ahead and continue looking for
Thank you, Maria.
the image.
Thank you. Okay, I'm looking. Sorry, it's easy. Ate a fruit. Step order. Maria, I'm going to also make you a co-host too, because I'm noticing that people are still popping in and out while I'm doing this. So I'm going to make you a co-host on the meeting.
I've been taking care of some people in the waiting room.
Okay, thank you. Thank you. Okay, then I'll keep hunting for what I'm looking for.
You have a great team.
I have a great team. Thank you for my great team.
And I would like just to say to all of attendees, we need your contact information. And at the beginning, also, we talk about the Virtual Graduate Study Consortium. You are invited. I am putting also in the chat window the links to what we are doing on standard development. We need students, academics, industries with us. Thank you.
Okay, I found one, but it's not Arduino. So give me 1 second. I need to find an Arduino one. I can show you on a Pico, but it may be more confusing than helpful. But keep wiring. This is the most difficult part of the wiring. After you have this wire, we're coding. We're done with the wiring. All right, I found one. I am going to escape out of here. I'm going to make a new slide and I'm going to put an image on it. So give me 1 second. Okay, so there's going to be more on here than you need, but hopefully it's helpful. So it's going to be the exact same stuff as this. And then hopefully I can't see the chat while I'm doing this. So hopefully my great team is taking care of the chat as well. Hamadou, Maria, and Luis, you're my great team. Okay, so I'm going to send you another image. And I made these images in Tinkercad and Fritzing. Tinkercad and Fritzing, if you're wondering how I make the images. Okay. And while I'm doing this, you should be able to look at the actual slides, since I know I am on a screen you can't see right now. Okay. All right, so I am going to go back to the slideshow. So like I said, there's some stuff on here there's a lot going on here, but the main thing I want you to see here is that this is your motor controller. This is your motor controller here. So one side, you're going to have left and right motor AB, and on the other side, you're going to have right and left motor AB. It doesn't necessarily matter so much the order right now, because if the robot is moving backwards or a way that you don't want the robot to move, then we just reverse the wires, okay? So what you're going to do is right motor to motor A, but you don't have these numbers on your controller, so that's what I was saying. So I'm going to take that out. And left motor to motor B, you don't have these numbers, so I'm going to take that out. And for the controller you're using, there is no standby, so you don't have to worry about that either. So now, so that's what you're doing right now, is you are putting the motor's on one side, and then you just need a ground. You need one ground connected. And then on the other side, you're going to put VIN to VM. That's that purple wire. You're going to put 5 volts to VCC. That's that brown wire. And then you can put the ground either here or on the other side. Then after that, there's going to be PWM B, bin 2, and bin 1. And you see the connections here. Then you're going to skip standby, and then you're going to do AIN1, AIN2, and PWMA. Okay, I am going to the chat now to see how everyone is doing. Okay, so there's your controller. Those of you who have a robot and are following along, give me an update, please, so that I'll know if it's time to move on or not. Hamadou, question for you. Where are the recording going to be? Because somebody did ask that earlier. Where are you going to post the recording?
Okay, IEEE Education Society, we have a YouTube channel.
Oh, it's going to be on YouTube? Okay.
Yeah, so together with you, we will try to edit this recording.
Okay.
And send it to IEEE Education Society official, not official, but administrative officials.
Mm-hmm.
They will help us to put on YouTube
Okay.
channel. I'm also inviting the satellite sites that got their kits.
Yes.
To produce some videos.
Yes, that would be great.
Sent to Carlota.
Yeah.
She's a great editor.
I'm a great editor.
Yeah, editor, video
Yeah.
editor, and so please help. So that is how.
Okay.
We are expecting to get in many countries like STEMist.
Yeah, that is great.
And yeah, and we would also like to know what is noir.
I made it up. Noir is a French word for black. So it's a black feminist. That means that well, you're still French. So that means that I'm a black feminist for STEM, black STEMinist. So it's a merge of several words. I promote STEM to brown and black people and to women and to diversify STEM. So that's the whole reason I put those words together. I trademarked that word. So I'm moving on because somebody said, how much time do we have left? We have 35 minutes left. This ends at 20 after the hour. And I want to make sure I at least get you to obstacle avoidance. Okay, so differential drive robots. When you have a differential drive robot, if you want to make it move forward, backwards, spin left, spin right, turn left, turn right, pivot left or pivot right, you control each motor individually. If I want the motor to go forward, this red dot represents the front of the robot. If the arrows are the same length, that means velocity and direction are the same. If one arrow is shorter than the other, that means the velocity is not the same. The speed is not the same, but the direction is. If one of them goes forward and one goes backwards, that means one wheel goes forward and one wheel goes backwards. Which of those images represents a robot driving forward? I just gave you a hint. Which of those 8 images, represents a robot driving forward? Top center. Very good, Luis. Backward. Which image represents backward? Top center is forward. Backward. Bottom right is backward. Okay. Spin left means the robot spins around the center between its 2 wheels. One way forward, one way back. Which one represents spin left? So they have the same speed. Very good. Bottom center is spin left. Spin right, spin right, spin right. Spin right. Yeah, hopefully, since you got spin left. Top left is spin right, spin right. Okay, turn. Turn is how a robot makes a circle. Turn means the wheels are going the same direction, but at a different speed. It either makes a clockwise circle or a counterclockwise circle. The turn left makes a counterclockwise circle. Which one is it? Turn left makes a counterclockwise circle. Top right. The difference in the velocities dictates the size of the circle. The bigger the difference between the velocities, the smaller the circle. The bigger, one of the first labs my students do is they have to calculate with math the velocity needed to make a circle of a given diameter or width. And they do that by measuring the width of the robot, measuring the distance between the wheels, measuring the diameter of the wheels, and they have to calculate that so that if I walk up to them and say, I need your robot to draw a circle with a 3-foot diameter, they should immediately have a function that they just type 3 in and the robot does that. That means they have already done in advance the forward or inverse kinematics necessary and the math to know what velocities to send to their robot to have it make a circle of a given diameter. That would be one of the first online labs I would do with students. How to apply these with 4-wheel robots. We probably have to get the kinematic model out for those. Honestly, I think it's going to be pretty similar though, right? Because you cannot have the 2 wheels in the back doing something different. Otherwise it ain't gonna make a circle. So you may have 4 wheels, but you got to think about which 2 are the drive wheels. And those other 2 may be passive wheels. That's a good question. Pivot left and pivot right. Pivot left and pivot right means the robot makes a circle whose radius is the width of the robot. The robot makes a circle whose width is double the width of the robot. The diameter of the circle is double the width of the robot. That means 1 wheel is not moving. Which one is pivot left? Pivot left.
Hello, are you back?
You're on mute, Carlota.
I think when my internet dies, it resets
Yes.
everything.
Okay.
You're back. Okay.
I'm so sorry. Yeah, that I have no control over that, obviously. My internet just acts up. Sorry. Okay.
No worries. We animated a bit during the time you were.
What you mean you animated? What does that mean?
We ask people to continue to wire.
Okay.
Yeah, we just do that.
Okay, sounds good. They kept us entertained.
I have a question for you. Have you used Omni wheels instead of caster wheels?
Not on this robot. I've helped students with Omni wheels like when I did first robotics, but I've never done Omni wheels on any of my robots. None of this stands for Omni wheels. So that means you got to do something totally different, right?
Right, yes. Do you see any value on Omni wheels for applications?
That would be cool. Can you if you add Omni wheels and yeah, in fact, that could be one of the labs. So that we need to put that in the chat. We need to capture that information as one of the things that we could do.
All right.
Some ideas also we are giving to students is if they think about security, how to integrate security in hardware security in mobile robotics. That can
absolutely, especially if you have virtual robots as well. How do you keep people from logging on so that they don't hack into your robot and do something nefarious?
So come back to us because these topics you can get some people that are working on it, and some students also are working on these issues.
Okay, sounds good. I'm just moving on. I still want to see some obstacle avoidance before we leave today. So, all right. So I've talked about how to do circles and square. I'll show you a quick one of this and then I'm moving on. I will make sure to capture all your great ideas in the chat. It'll go in my final report.
Figure 8.
So after circles, we do a figure 8. This robot has a lot of odometry error, but I will, that's an example. So my students will do squares, figure eights. We'll talk about odometry error and that you have to use encoder feedback to correct for odometry error. Odometry error basically means as the robot moves, it gets off more and more from being able to hit its goal. Okay, so now you have, in theory, wired your robot. You've wired your sonar and one LED, okay? I will let you know right now, do not upload any code to your robot unless you have it on a test stand. Otherwise, you will drive it off the table and it may drag your computer with it. The other thing I will tell you is that a good habit to always do in your code is insert a 5-second delay. So in case you want to drive your robot untethered on the floor, if in your setup function you insert a 5-second delay, you know you always get 5 seconds to get it unplugged and on the floor before the robot moves. But you always want to do something to make sure that when your code runs, it will execute immediately and that you don't drive the robot off the floor, drag your computer off your desktop, etc. Okay. I am now going to show you a simulation of this, and then I'm going to Tinkercad and walk you through the code, and you can now download that to your robot, okay?
Proportional control, simulation testing, buzzer, LED, and motor speed. Change with distance from sonar.
So it's hard to see, but as this distance to the sonar is changing, the RPM, so loud. Hold on. As the distance to the sonar is changing, the RPM on the motors is changing, and the buzzer and the LEDs are changing based upon the distance as well. So I'm now doing obstacle avoidance, but also showing visually with the LED and with the sound that the buzzer that the robot has detected something. So that's what's happening here. I'll turn the sound back up. Okay. And then here's what it looks like on the actual robot. I have it. This is my test stand.
LED and motor control. Sonar.
So the LEDs are changing. The robot's wheels are changing, and it's making sound, even though it's kind of hard to hear it. It's also making a sound. So this is also an example of how I multitask. I was actually at a book fair selling books, programming robots. So that's why the background looks like that. I was in a Barnes and Noble, if you guys know what a Barnes and Noble is. Okay, so
proportional control.
Moving on. I think we're ready to go look at the code. I'm trying to
simulation test.
See what my next slide is. Why is this going crazy?
LED and motor speed.
Hold on.
Change with distance from sonar.
Sorry about that. Okay, I was going to ask another question, but I think I want to do some coding. We have about 20 minutes left. I want to do coding, and we're going to end with this last question in the chat. So before we do that, let's go to Tinkercad and make sure everybody gets their obstacle avoidance working, and then that'll be my conclusion, and then my workshop will be done. So let's go to tinkercad.com. We're going to go to that classroom that I mentioned before. And remember, if you don't have an account, you can create one. So I'm logging on. And I also do 3D printing in here. So Tinkercad, I do 3D printing because my robots are 3D printed. So sometimes we design the files. Like you may notice, this is one of the files you got for your robot. You have a microbit. We also have code. So here's some of the simulated code that you saw. And now what I'm doing is I'm going into my classroom that says Robotics Workshop. This is the link that I sent everyone. So whenever I do a robotics workshop, I use this link and this code, and I'm putting it in the chat again so that you can now get into my Tinkercad classroom. And I'm going to go to activities, and I'm going to go to the activity that we can use for obstacle avoidance. So that one is Arduino sonar for distance sensor 2D. I don't think it's 2D. 2E, no. Where's 2F? It should be 2F. Where is 2F? It might be this one. Don't remember. I haven't done this in a while. No, that one doesn't have the motor. I need the one that has the motor and the obstacle avoidance. It may be inside of here. Let me see, make robot move. So it's probably this one, and I'm going to have to integrate it. So what I'm going to do is I'm going to show you this one, and I'll probably have to integrate the code inside of arduino.ccc to show you what happens. Okay, so I'll put it in the chat for you. So you click on Tinker this, and it will open up the code that you can use to drive your robot. And then I'm going to show you how to integrate that with the sonar to do obstacle avoidance. I'm not sure why it's so slow. I'm praying my internet is not about to die again. Has anyone been able to?
I think. Judith.
I'm sorry, everyone. I don't know why this keeps happening. It's not even raining here. I don't know why my internet is acting up so bad. Thank you for coming, David.
I just said maybe because you are very popular and today you were packed.
So yeah, so let me just quickly show you how to do this so we can wrap up because we have 20 minutes left. Okay, so inside of here, if you go to the code, you click on code, the code in here shows you how to make your motor.
Please share your screen.
Oh, okay, sorry. Sorry, I forget it all turns off every time I do that. I do apologize. Okay, so if you go in Tinkercad and you go to that program, the link I just sent showed you. Although it doesn't look like there's anything happening here, I really did this to give you this code. So this code is what you need in order to make your robot move. Based upon how we've wired it, if you run this code, your robot's going to drive forward and backwards. So what you want to do is copy this code into Arduino. So I'm going to go, so you're going to copy it into, let's see if I can get the internet back. You're going to copy this code into arduino.cc. Let me put these links in the chat for you. And if I'm going to just send this link directly. So you're going to take this link, open it up, get the code out of here. And you're going to go to arduino.cc. I'm going a little fast, so let me know if you can't keep up. And once you're in here, you're going to have to create an account. I don't think it'll let you code without an account. So you're going to go in here and I'm going to sign in. You can sign in with, I'm going to sign in with, I have several accounts. I'm going to sign in with this one because one of them I probably already have the code in here. Okay. Once you sign in, you're going to go to software, go to cloud editor, software, go to cloud editor. Some of you said you had already been programming, so you probably are past this point, but go to cloud editor. Okay. And now the code I just copied, I'm going to put into a new program. What I was saying before is that even if you do the cloud editor online, it's going to make you download an agent to talk to your robot. Okay. So that's what you've got to do is download that agent. But let's assume we did that. Like I said, my robot's not even up here with me. So I've done this before. Here's now where I have copy and pasted this code into a new program. I've copy and pasted the code. The first part of the code is just where everything is connected. So AN1 is on 8, AN2 is on 9. This is the exact place where you connected all of those motors. Okay. Down here, I'm just putting in some numbers to vary robot speed. Robot speed can be anything between 0 and 255, okay? When you get too far below 100, the wheels just don't move. They don't have enough startup current, but something between 0 and 255. So then what this does is this sets all my pins as an output because they're going to send the voltage to the pins, and based upon the order in which they send it, it will make the motors either move forward or backwards, wait for 5 seconds, and then stop. Okay. So you can change these based upon that image I showed you to make the robot drive forward, backwards, spin left, spin right, turn left, turn right, etc., just by setting those as high, low, 0 speed, etc. Okay, so what you would do next, and like I said, I can't do it because I don't have my robot up here, is when you plug the robot in your computer, it's going to tell you it found an Arduino Uno and on what COM port where it found it. At that point, you click upload to upload this code to your robot, and the robot should move. If you don't have an agent, it will come up and say you don't have the Arduino agent on here, and somewhere over here, it'll say install the Arduino agent, and you have to install that on your computer in order to talk to the robot. I want to stop here and make sure there are no questions. Has anyone gotten their robot moving either before today or today? You can put it in the chat or come off mute. Okay. Nobody has the robot moving yet? So as long as the robot is plugged in your computer, it should move. Once you unplug it, you're going to need to use the battery pack. You use that 9-volt battery pack, and if you plug that battery pack into the back of the Arduino and slide the switch so that it's on, whatever code, okay, good, FAU has it moving. Whatever code you wrote will automatically just run on that microcontroller until you change the code. FAU, did you get obstacle avoidance working? Harry?
Hello, can you hear me?
Yes, Harry, hi. Did you get obstacle
Hi.
avoidance working?
Yeah, we got that working, but I actually tweaked the code to do the opposite, so it actually chases whatever's in front of it.
I need a video of that, Harry, please.
Just sure, yeah.
Send the video to me or Hamadou. I'd love to see that. I want the code and the video.
Okay.
That is awesome, Harry.
Thanks.
Okay.
Yeah.
All right. Well, let me keep going.
Just let everybody know also, I think it's also Harry doesn't know. He's among the 3 students we selected for an award for contributing to IEEE standard use cases.
Congrats, Harry.
Oh wow, thank you.
And
Harry,
I'm
did
so
you
honored.
know?
yeah, he didn't know, I think. It's just now that I'm announcing it, but Maria and Luis Felipe already know. And we have also from Ero, Luis Felipe.
Yeah. Did Luis Felipe gone?
Yes, I'm here. So we have also here connected Michael Stalford, that is from our group in Embry-Riddle Aeronautical University. And he's also one of the 3 recipients for this award.
Yay, that is awesome. Congrats.
Yes.
And the third one is Gupta from Sam Houston University. So we are encouraging students to contribute to our standard development.
Awesome. Okay, I want to show, because in the next 10 minutes I want to wrap up. So I want to show one more code. I want to show the obstacle avoidance code, even though Harry said he tweaked it. Maybe Harry can tell us how he tweaked it if I can get it open. Let's see if I can find my obstacle avoidance code on here. It may not be on here. Sonar. Let's see what's on this one. I need to name my code better. Oh no, that's not Sonar code. I don't know what that is. Okay. I don't know where my Sonar code is. Okay, so I'm going to show you a place that I had mentioned earlier. So when I make examples of things working, I always put them on instructables. So that's another great way for you to quickly get to the code. So if we can go find the Arduino robot in here and find the obstacle avoidance code, then I can just get it from here. So if I go here, I did obstacle avoidance on here with 4 sonar. You don't need the 4 sonar. You can get the code out of here and just delete the other 3. So if I go down here, inside of here, you can copy out the code. And inside of here, it actually has the code for reading the sonar and obstacle avoidance. So that's what I'm going to do is I'm just going to copy this code out of here and use this code. So just like I did for the motor, you would copy this into a new sketch, and then you just modify it how you want to make the robot work the way that you want, right? So I'm making a new sketch, and I'm going to call it obstacle avoidance. And the other place you could probably get it is I probably do have it in Tinkercad somewhere as well. And now, like I said, because you have 1 sonar, you would just use this get distance function, and you would attach this to whichever sonar you have connected. And you now run this code where it reads the distance, and based upon the distance, it changes the lights, but it also would then move the motor, okay? So that's actually the one for the lights. That wasn't the one for the full motor. So I copied the wrong one. I will get the right one out of here. But it's this one. And actually, it's Lilybot sonar sensors here. And you can click on this link and download it. I'll put this in the chat. You can click on this link and download it and then upload it into the cloud editor, or you can copy and paste it. It's your choice, okay? So if I download it, I can then go into the cloud editor and just upload that code. I can go over here somewhere because I haven't done this in a while, but there should be a way in here to open it up. Import local file. There it is. So you would then import. I'll go to downloads. And I don't know where it downloaded to. It should have gone to downloads. It did not. But basically, you would find it and then upload it. Okay, I'm going to stop here because I want to make sure we get our final feedback before we hop off. If you have any questions or if you need anything, you can reach me on my last slide. So I'm going to go to the last slide, but before I go there, I want you to put in the chat your final feedback. How could you use Lilybot, not just robots now, but what you've seen of Lilybot in online labs, in your classes, in academia, what kind of learning activities? So building on what you already put in the chat, thinking about this open source robot with modular controllers, modular programming methods, 3D printed parts. How could you use this in online learning to clean up a mess, back to the vacuum cleaning robot. So put that in the chat. And while you're putting that in the chat, I am going to read my conclusions, put up my last slide so that you have all my contact information. So what we have seen here is that robots are great for illustrating multidisciplinary connections between disciplines, as well as great for use for teaching STEM and STEAM. And I noticed somebody put medicine on the end. STEAM is now medicine and math. Open source robotics is great for increasing access and inclusion in STEM by lowering costs, sharing resources and knowledge, and robots can be used in online laboratories to teach hardware, software, and electronics. 2 robots playing tag. I love that. Using infrared remotes to do that. All right. Also put some of your key takeaways. Put some of your key takeaways in the chat. Not just ideas for using robots for online learning, but also, what are some of the key takeaways from the presentation today? What did you learn today? Did you learn anything today? The good, the bad, and the ugly. And here is all of my contact information. Okay, what did you learn today in the chat? How could you use robots? How could you use Lilybot in online learning? What are your key takeaways from the workshop today? Great explanation of PID. Thank you for that. And here's all my contact information. It is also on the slides. So as long as you have access to the slides. Okay. We are about 5 minutes from wrapping up. Please keep putting all your feedback in the chat. I will get the video downloaded and edited into Hamadoo. I will get the chat downloaded and put into my final report. And I'll email that to Hamadoo as well, and Lewis. And connection between controls and, that's right, controls and robotics are very closely related. I'm a controls engineer as well. I worked as a control engineer before I got my PhD in robotics. So controls engineering and robotics are very closely related. Yeah, so great feedback flowing into the chat right now. My contact information is on the screen. And I am done. I want to thank you all for being attentive and listening. And I hope you enjoy your Lilybot. I cannot wait to see all the great things you do with your robot that I have not done yet. But I want to turn it over to Louis and Hamadou to have the final word. Thank you so much, Y. Thank you all.
Okay, thank you very much. Great presentation. Luis Felipe, do you have few words?
Thank you, Carlota. Thank you, Dr. Hamadou. Thank you, everybody that was connected. We need more time, is what I can say. We need more time, and I think it's on everybody just to get your kit and spend the weekend. I can spend maybe hours and hours running examples, changing the code. I, for example, was changing the function in one of the examples that had an array for reading the 4 distance sensors and just making a simple get distance functions as you presented there with just one instead of going through each of the index of the array, just going targeting one specific sensor. Or if you have only one LED, you don't have to do that array of 4 indexes, and you just can just configure one LED. So you can start changing the code, the examples, and trying to match what you have and what the example does. The first thing is make sure the pins are the numbers that you are using, because it's not going to work otherwise. Make sure you have start with the very simple, just motors rotating forward, and later you add the sensor or configure the sensor individually, and later the motion, and later combine them and do a good application. It's really interesting, very fascinating, and I will keep following you, and I hope everybody in this room also will keep following you in social networks and workshops. And we are really glad to have this time with you and with all the people connected. Thank you.
Thank you all so much. Hamadou, any final words?
Yes, thank you. Thank you very much for your time, for volunteering for IEEE Education Society. Carlota is also a fellow of IEEE American Society for Engineering Education.
Yes.
And awardee and awarded by Education Society too.
Mhm.
And Carlota is also a distinguished lecturer. That means if your society, if your chapter in any region of the world need Carlota to travel and give a talk, if you are a chapter or student branch, just like you can request a distinguished lecturer, and the VP educational activities of IEEE Education Society can help maybe for the travel grant. Thank you very much for all. I posted in this in the chat the link of what we are doing on standard development.
Mhm.
And I show that through Virtual Graduate Studies Consortium, we were able to get some students, undergraduate, graduate students, to contribute and finish their thesis through the collaboration we have together. So Maria is an example as an academic contributing to this process, and also Luis Felipe was a student and now professor at in Arizona State. So yeah. So he's Luis Felipe will be happy to give back to the student here in this talk. And also I posted a conference, a symposium on security related also to online laboratories and online teaching and learning, ISDFS. We have few grants for registration, those who will submit a paper and register. If you need more information about ISDFS, please let us know as soon as possible. Thank you very much, Carlota. We greatly appreciate it. Carlota wrote, share your videos, share your experience, and thank you very much for your attendance.
Thank you, everyone. Bye-bye.
Thank you.
Thank you, everybody.
You.
Bye.
Thank you.